Hello, Physics 20. For a minute here, I'd like to go over masses on springs, okay, and how their movement actually explains or defines simple harmonic motion. So, in these notes here, I have a whole bunch of detail here. If you can kind of follow the diagram, I don't need to necessarily read everything. Um, but if we have a horizontal mass spring system, when we set these up, they're always frictionless, so there's no friction. And I just want you to notice how the force, the restoring force, and the velocity, and the acceleration, all three of those, how they change throughout the movement. So in this, if you look here in the first one, here we've displaced the mass to the right, and at that position, we have a maximum acceleration. Okay, the mass wants to go back towards equilibrium, and of course that's proportional to the force, right? So the force and the acceleration are proportional directly to each other, but out there the velocity, it would come to a stop, and the velocity would be zero. As it comes back, though, it's very dynamic, of course, because the force is changing and the acceleration is changing all the time, as is the velocity. But when you get to the equilibrium position, the velocity is now at a maximum. It's now going as fast as it ever goes in this direction. Okay, it's actually moving very, very fast in that direction. But at that point, as you note, the force is now zero. The spring in this position here, the spring is happy to be there. That's the equilibrium position of the spring. And so the restoring force is zero at that point, which also means that the acceleration is zero. But, a few seconds later, the mass has passed that point, and now it has compressed the spring. You see that here. And the spring wants to go back towards equilibrium. And so you have a restoring force, Fr, and you have a acceleration. But at the maximum displacement, there you would have a velocity of zero. And if you remember this displacement, I guess we should note that too. Here, the displacement is positive, and then down here, the displacement is negative. But, when you have a negative displacement, you have a positive force. And then when you have a positive displacement, you have a negative force. Okay, negative force. So hopefully those kind of make sense here in terms of how this would move. You can visualize that in your head. And that just goes back and forth, back and forth. If we, worth noting here is this maximum displacement. Typically we use x for our displacement, but as you remember before, we're going to start using a for amplitude. And this is a term we're going to use to describe the maximum displacement, okay? And that'll show up in some of our formulas. Now, we could also look at it vertically. The same thing kind of happens, and it's kind of worth, actually, it's worth kind of following here. So in vertical movement, we could take the mass at its squished position here, and if you can follow this, see the force up from the spring is much less, okay, than the force of gravity down, okay? So then the net force would be down, and you can see that here and here, that's negative acceleration, but you're at a velocity of zero, okay? If you go to this part though, this is now where the mass has returned to its equilibrium position, and here you'll notice that the force of gravity is equal to the restoring force from the spring, okay? But just for that split second, the forces are balanced, so there is no force on it, but you've now got a maximum velocity right there, okay? For sure you do. Okay, and then over here you can see that the arrows just start changing places. See, the force of gravity never changes, but now the restoring force from the spring up is greater than that, and so the net force is up, and at that point the mass has come to a stop. Okay, so it shows the maximum velocity there being zero, and then that pattern just keeps repeating itself. Okay, so it goes back and forth, back and forth. I guess just worth showing you here. Maybe I'll just pull this up. If we look at a horizontal mass spring system, it would look just something like this. The idea behind it is that you'd have areas where if it'll load here for me, I know I have some difficulty doing this before. I'm doing lots of things at once here. So yeah, there we go. So you can see that the mass, the zero position is faded, but it goes back and forth from about a 2 + 2 to a -2. And if it was a frictionless system, that would happen, indefinitely. Okay, so actually, I do want to show you another one here. So if I can get that to calm down, I'll maybe pull that up again in a minute. So the point of showing you that pattern is you just need to know and understand the movement, the simple harmonic movement in a spring, because that movement actually is also the same in a pendulum. So here's kind of the compression right here, and I really like this one. It shows a mass oscillating system at the top here, and we've already visualized that going back and forth. When you're at position C here, okay, we can actually map that on an acceleration displacement graph. Okay, so an acceleration displacement graph, that's what this first one is. All right, and if we note here, when the mass is at position C, that's a positive displacement, a maximum displacement. But at that point, you have a negative velocity, or a negative acceleration. Okay, at that point, the mass wants to go back to equilibrium, so the restoring force is negative, and so the acceleration is negative. Then as you come back here to position B, if the mass is right here, you'll notice on the graph that the acceleration has reached a 0. It has come from a negative back to a 0 because there is no acceleration at that point. And then we look at position A, and the acceleration is now positive. See, so it's above this x-axis here. Okay, sorry if you can see that. So we now have a positive acceleration. Down here, I had a negative acceleration, but up here now I've got a positive acceleration. And I get a positive acceleration when I have a negative displacement. Okay, so on the x-axis, if the x-axis is negative, the y-axis is positive. And I'm going to erase all that so you can kind of see the whole thing again. But this means this relationship is showing you what happens to acceleration when a mass is oscillating back and forth on a spring system. Now, worth mentioning as well is the velocity. And really, I guess this really should be a speed displacement, not velocity, because I realize that because the velocity vector it's flipping from positive to negative. But here it just shows that the velocity is always positive, which it isn't. So this is probably better known as a speed displacement graph. But anyway, sometimes they'll just refer to it as velocity. The point is, you'll see that when you have a maximum displacement out here, okay, at position C, when you're at a maximum displacement, your velocity is back to the x-axis. So you have a 0 velocity right there. When the mass has come back to equilibrium at position B, that's where you have your maximum. And we're going to actually learn that formula today, V max or whatever, the maximum speed. That's the point in its movement where it's moving the fastest. And then, obviously when it gets over this way, now the spring is getting compressed, and so the speed drops down to 0. By the time you get to position A, the velocity is 0. So anyway, I think if you visualize that, I don't think that's horrible. In your mind, you're kind of just mapping what the heck is going on with a mass spring system. And those are the general, I guess, principles behind the movement of a mass on a spring. So let's just dive into the math. There's really just 3 formulas you need to know that explain the movement of a mass spring system. Okay, and here they are right here. So let's just dive into these. At any point in the movement of the spring, if you have a restoring force, we could exchange that. We call it Fr, but the restoring force is going to be the net force. Okay. There are no other, there's gravity acting downwards on it, but that's being canceled by the normal force. So the unbalanced force on the system is really coming from the spring. So we can say then that the net force is being caused by the spring. So we can say that F net is equal to Fr. And that simply expands. F net is just M times A net. I guess we could add that if you want, but the mass times the acceleration will equal a negative kx. Okay. And this isn't on your formula sheet, but both of these guys are mass times acceleration and negative kx. So if we're looking to solve for the rate of acceleration, it's a really simple derivation. It just means that a is equal to a negative kx over m. All right, so as soon as you recognize that, and I'm going to give you a lot of practice problems that will get you to see this, but if you need to solve for acceleration, this is the formula that will do it, okay? And it's worth noting that if, again, I keep mentioning this, but if you're ever dealing with an amplitude, okay, if it ever gives you an amplitude, or A even, and it wants you to know, I guess that's big A, and you're trying to find little a, you're trying to find the acceleration. If you know what the amplitude is, you substitute that guy in right there for x, because a is just a special x. I think I've mentioned that a little bit, but I'm hoping that's starting to click. Okay, so amplitude is just a special x. But yeah, you could throw it in there if you know the, obviously x though, if it's positive or negative, it's going to change this value, and the acceleration would then be, either negative or positive in the reverse, right? Okay, so that one's not too bad, I don't think. That's the very first one. These other qualifiers down here are listed just to help you recognize that. The acceleration is always changing. I'm just checking this. I don't think we missed anything. X, oh yeah, this one does talk about x when x equals the maximum. That would be the amplitude. So the maximum acceleration would occur with the maximum amplitude. I guess that makes sense. Okay, so that's the first formula. The second one deals with how do we determine what that maximum speed is at equilibrium. Okay, how fast is it going when it reaches this spot, that spot B right in the middle? How fast is it moving right there? Well, it turns out we can solve for that using the conservation of energy, because what we can say is, and I kind of sketched this a little bit, we can compare the total energy that the mass has at its maximum displacement. We can compare that to the total energy that it has at equilibrium. Okay, those two positions. And if, as most of you did really well on this in the test we just took, we can say that EM1 here is going to equal EM2. Okay, if it's a isolated system, there's no friction, no problem. EM1 equals EM2. So I kind of cheated a little bit. I started drawing this already. It means then that out here in this position, the total energy is elastic potential energy. It's 1/2 kx squared. It's not moving at that point, but it's got a whole bunch of stored elastic potential energy. When you get to the equilibrium position, it doesn't have any elastic potential energy anymore, because now it's back to equilibrium, but now you have kinetic energy, 1/2 mv squared. Okay, so all we do here, and you can see this derivation, we just make those two equal to each other. 1/2 mv squared equals 1/2 kx squared. But if we are dealing with a maximum velocity, we get that by having a maximum displacement. So you can see here, look, this x got replaced with an a. Okay, so that's where we start using a. Now, it kind of did skip a step here. I guess I could, I started writing it over here, so I'll just finish it for you. The 1/2 is the same on both sides. Okay, so we can just cancel that out. So now you have mv squared equals kx squared. And sorry, I forgot to change that. We're going to change that x to an a for amplitude, because it's a special x. Now we are trying to solve for v max here. So what I would do is divide by m, divide this side by m, and then in an intermediate step, I think most of you are seeing this, it's going to be ka squared over m. Okay, and I just wanted the v max, so I've got to square root both sides. There we go. Here, I'm going to give yourself some more room so you can see the rest of it. And I'm left with v is equal to the square root of k times a squared over m. Now, that doesn't look like the formula that I showed you earlier, because we could simplify this one more step. If you're square rooting a squared, we could factor that out because the square root of a squared would just be a. So doing so means we actually simplify this one more step. So we'll say the velocity, we bring that a out in front, okay? Because if I square root the a squared, it's just a, but I can't simplify the k and the m variables because they were square rooted. So there it is right there. So the acceleration, or sorry, be careful. Big A is amplitude. So the Vmax, the maximum velocity, is going to equal the amplitude times the spring constant divided by the mass. Okay. And yeah, it's written a little neater right there. So, but actually, I think on the formula sheet, I did put the word maximum. Sorry, that's so small. Oh, that doesn't look good. But it's Vmax is equal to the amplitude times k over m. So if you know you're calculating the maximum velocity, if it's a spring system, you just need to know what k and m are and put them in carefully, and you're on your way. So the last one, this one has a really cool comparison to circular motion, and it's the period. So for a mass moving back and forth, how do we determine the period for that movement? Well, as it turns out, we can actually compare the movement of a mass on a spring. Okay, you can see that. Actually, here, let me just highlight that here. You can see that down here. Okay, here's the mass on the spring. It's down there. And then here is a mass that's going in circular motion. Okay, and on purpose, we have the radius, if you can see that here, the radius of the circle is the same as the amplitude of the mass spring system. Okay, so you see that? They line up perfectly. Now that's done on purpose because if you observe a mass that's moving in circular motion from a certain point of view, it will match the movement of a mass on a spring that's moving horizontally. So here, I'm actually going to try to carefully show you this. And I'm really taxing my computer here to see if I can do all this stuff at once. So if you were to visualize this, this is what it would look like. And it's a little bit trippy. So I'm going to try and blow this up and see if it will play it still. Looks like it's getting there. Okay. So if you look at this mass, whoa, it's going to restart here, I think. There it is. Okay. So if this mass, look at it, is going up and down. Okay, so this is representing a mass on a spring, but I tricked you. This is actually a mass that's going in uniform circular motion with a radius that matches the amplitude. So you can see it now here, it looks really obvious. Yes, this is a mass that's going at a constant speed in a circle, but then we're going to rotate it, 90 degrees and look down the plane of the circle, and you can see this doing more and more. Bang, there it is. That right there is the movement of a mass on a spring. It's one of the coolest parallels in this kind of motion. I think this oh yeah, here we go. This graphic shows it even better. So we're looking at it from the side, but a light source shining down the plane of the circle would do the shadow on the right. So the shadow on the right, or I guess I'm moving into this one, the blue mass on the right is matching the position of the black mass that's orbiting in a circle. And so the period, this is the point though, the time that it takes for the mass to go all the way around is the same as the time it would take for the blue mass to oscillate up and down and all the way back. Okay, so the periods match, and that's the cool symmetry behind this concept. I'll maybe clear that out here so my computer doesn't crash on me. Oops, sorry. And we'll get to this. Okay. So that means, yes, so their periods are the same. So let's look at the math here. I kind of started doing it over here. So if we look at the velocity for a mass that's moving in a circle, we learned this for circular motion, it would equal 2 pi r times the period. But we're going to modify that a little bit because this mass that's going in uniform circular motion here, the radius of that movement matches the amplitude of the mass on a spring. Those are the same distance. So for the spring, we can change the maximum velocity for the spring to match, it would be 2 pi times a over the period, okay? So these two are, I just swapped amplitude for the radius. They're really a distance, so I'm not breaking any rules by doing that. But this is the clever adaptation. Now what I can do is I can say, fine, if I can express Vmax, and this one's on your formula sheet, you can express Vmax as 2 pi a over t, then that means that I can make that equal to the formula that we just derived earlier, which is this guy right here, okay? Amplitude is equal to the square root of k over m. Or sorry, not amplitude. The maximum velocity is equal to the amplitude multiplied by the square root of k over m. So setting these two formulas equal to each other, I'm really saying that Vmax is equal to Vmax. And what this enables us to do is get rid of the amplitude. And that's what's really interesting. For a mass spring system, as long as you're not deforming the spring, the amplitude doesn't matter. It doesn't matter if you pull the spring just a little bit this way and then let it go and let it oscillate, or if you pull it a long ways and then let it go and let it oscillate, the period will be the same, okay? Now, I know that's maybe hard to visualize in your mind, but that's exactly what happens. So in this case, we actually can simplify this. I'll just do it quick because you can see it in the notes. So I'm going to solve for t. So basically, I'm going to multiply this side by t and multiply this side by t, and then divide by the square root of k over m to move that guy over here. And then when I'm done, I have t will equal 2 pi divided by the square root of k over m. Okay, now that actually isn't what the formula looks like, because we can simplify that a bit more, because I've got a fraction here in the denominator. I can reciprocate that. So flip it, and put it in the numerator. Okay, so if I flip it like this and put it in the numerator, then it would be t is equal to 2 pi times the square root of m over k. All right, see how I flip that? And there she is. So the period for a mass on a spring. So this is what you got to separate, right? Don't be using this for a pendulum, because pendulums have a different formula, if you remember, right? But it does look similar to a pendulum. In fact, there's a great video I posted that video, just the last 10 minutes of it, with Walter Lewin. Love it, love it. It's a classic physics explanation of the comparison between masses on springs and a pendulum, okay? So, but if you have to calculate the period for a mass on a spring, this is it, okay? So m, of course, is the mass, and k is how stiff the spring is, so the spring constant. And again, I'd encourage you to watch Walter Lewin's discussion on that. He has a great job of comparing and contrasting the two formulas, this one here being for a mass on a spring, and the other one being for a pendulum, which is L over G, 2 pi times L over G. Okay, so those factors there, I guess I listed those. We talked about that. The amplitude does not affect the period. That's really cool for a mass on a spring. So I want you to carefully just make your way into those practice questions. You will be using, and you're probably seeing it now on your formula sheet, there's a whole section there that's just for simple harmonic motion. So if you're dealing with a pendulum, you go to those formulas. If you're dealing with a mass on a spring, you go to those. And I think you'll have any difficulty starting to figure these out, because they actually make a lot of sense when you start to break them down. So carry on with that, and check your answers as you go. Let me know if you have any questions.